Okay, in this video we'll be looking at another way to transform graphs. Last time we looked at moving them around, we called that translation. And this time, I'll just tell you straight away, instead we'll be stretching and squishing graphs, and we call this dilation. That's the fancy name for it. And we'll do this to a trig graph because it comes with some special properties that you need to know and that are mostly controlled by different dilations, so we may as well knock that out together. Okay, so we'll start with a graph of y equals sine x. It's a wave that bounces up and down around 0. You can easily build this wave by spinning around the unit circle and tracking the y value for sine. And just some preliminary properties. We say it has an amplitude of 1. That's the distance from the center of the bounce to the edge, which is clearly 1 right now. Okay. The period is 2 pi. Now, what does that mean? Well, when we do trig stuff, we like to think of and talk about x as some measure of time. Okay, well, I like to think of it that way. The period is the time it takes to do one complete cycle of the wave. So see how this cycle repeats, and the time it takes to do each of these cycles is 2 pi. Of course, you should know this corresponds to taking 2 pi angle to spin one complete cycle around the unit circle. So what happens if we change to 2 times sine x? Well, like from last time, this is something directly controlling the y value. In particular, it doubles all the y values, so everything would appear to stretch vertically taller like this. Some key points to notice. Y values of 0 stay at 0, since of course doubling 0 is still 0. The maximum value of 1, because the amplitude was 1, right? So the maximum value of 1 will double to 2, and the minimum value of -1 doubles to -2. In other words, the amplitude has changed. Okay, it's now 2, but nothing else has changed. So let's bring things back to normal, and this time we'll think about putting the 2 inside the bracket. See how in this equation, it's still y equals sine of something, but this time the x has changed into 2x. And so from last time, that's a transformation of the axis, not the graph directly. So rather than stretch out the graph, we should stretch out the axis. Okay? And so see how now, in 2 pi time, we are able to complete 2 cycles. We're traveling down this wave twice as fast. And if we once again rescale things back to the original sort of view, we see that the effect of going twice as fast like this is actually to horizontally squish the graph by half. Now, one complete cycle only takes pi time, so we say it has a period of pi, not 2 pi anymore. And again, that means that every cycle as we travel along the wave only takes pi time, not 2 pi. Okay, and that's what the period means. Okay, so let's see both directions of dilation again. Multiplying the y value by something directly stretches the y value. So in the case of a trig graph, it stretches the amplitude, as shown in the red dotted line there. Multiplying the inside stretches the x-axis, which has the effect of squishing the graph horizontally. For trig graphs, we can think about moving faster or slower along the wave. Right? If it's, say, sine 3x, then we can see that in 2 pi time, we've travelled 3 whole cycles. In other words, well, each cycle would take 2 pi over 3 time, and the period is 2 pi over 3. If, on the other hand, we halve the x inside the bracket, we do the opposite. We squish the axis and therefore stretch the graph horizontally. This has the effect of moving slower along the wave. We see that in 2 pi time, we've only travelled half a cycle. It actually takes a whole 4 pi to do one full cycle, so the period is 4 pi. Okay, in general, the period should be 2 pi divided by whatever the x is being multiplied by, as we should have seen then. Okay, we'll finish by putting fancy names to everything, writing it all out. We've seen most of them already, but let's just pull apart this equation here. Y equals 4 sine 3x. First, notice it's 4 multiplied by sign of stuff, so those y values are being stretched 4 times as big. This means the graph vertically stretches 4 times bigger, since it's the y values. We call this a vertical dilation with a scale factor of 4. In particular for trig waves, it makes the amplitude equal 4. Okay. Now what does the 3 do? Well, as we discussed, it stretches the x-axis 3 times as big, and the effects this has visually on the graph is it appears to squish 3 times smaller horizontally. We call this a horizontal dilation, with a scale factor this time not of 3, but of 1/3. And we need that reciprocal, that 1/, because things are squishing smaller rather than stretching bigger. Okay, for trig waves, back from the unit circle, x normally needs to travel 2 pi to do 1 complete cycle. But if things are horizontally squishing 3 times smaller, then x only needs to travel 2 pi over 3 per cycle. So as we mentioned before, the period is in general 2 pi divided by whatever number is stuck to the x there. Now, I never actually remembered this when I was doing it. I would always sort of think through, it takes 2 pi angles, so that means that the amount of x needed to travel 2 pi angle should be 2 pi over that number. And I hope it makes sense to you. Okay, I wouldn't take this as something to memorize, but something to understand, just because of how that number is transforming the equation in the graph. Okay, so that's dilations, stretching or squishing the graph and or the axis by multiplying numbers. Okay, again, just be careful with whether those multiplications are directly controlling y or x values, or whether x or y themselves are being changed. Okay, that affects whether it's the graph or the axis that is stretching or squishing, and therefore whether the effect on the graph should be reversed or not. Okay. So thanks for watching. Feel free to ask further if you have questions. I'll see you around. Bye.